Good afternoon. Myself, MD Atikur Rahman. And today I'll be talking about Borassus husk fiber reinforced epoxy composite and its experimental analysis of physical, thermal, flexural, and dynamic mechanical properties. And we'll also look into whether it is suitable for high performance applications. To derive the whole presentation, I make some of the sub-contents so that it would be easier for the audience to get the essence of the presentation. First, I'll be talking about the tree itself, which is known as the Borassus flavilifera, and its typical uses. Second, I will talk about the biofibers in modern engineering application, method used in this particular research, properties of Borassus husk fiber at its treated and untreated state, properties of Borassus husk fiber reinforced epoxies, and then we'll go to the summary. Along with this one, I will briefly talk about what the novel parameters we have introduced during this research work. And I include references so that we can see which of the references I use for this presentation. First, we'll look into the tree itself, Borassus flavilifera. That is the scientific name. In our South Asian region, this is also known as the Palmyra palm. A lot of people, they call this as a wonder tree because generally in our South Asia, we use it for 800 purposes, although I did not include quite a lot. First, we'll see this is like a single cylindrical tree, and they have a trunk like around 30 meters long, and its vertical root can go up to 15 meters downwards. Therefore, it has an incredible capacity of retention of the water and soil, which helps in the soil erosion, protect the soil erosion actually. It can also planted above the 80 meters above from the sea level, and it has a varied temperature it can sustain from 0 degree to 45 degrees centigrade. Then the conventional uses we use for the fruit pulp, which is using for delicious sweet food. Apart from that, some of the medicinal purposes we use this fruit pulp. And the particular research, the particular interest we have drawn for is fruit shell, which is known as the husk as well. Currently, it has been using as an agricultural residue and fuel. However, that's why we want to investigate its properties so that in the future we can incorporate this one in modern engineering application. So let's see some of the biofibers are being currently used in engineering application. First, I need to talk about the Airbus A320-200 wing box was constructed using a Remy fiber reinforced polymer. Within this one, the weight been reduced 14% compared to the conventional aluminum 7000 series. Apart from that, flax fiber reinforced polymer being used for the tail plane, cabin door, partition panel, tray tables, and so other internal structures of the aircraft. And last year, 2024, first wooden satellite was introduced, named was Lignosat, that was jointly worked by the SpaceX and one Japanese university. And that wood was derived from the Honoki species. And last but not the least, car parts, actually internal structures such as dashboard and other cabin door or the compartment that been used for the hemp, sisal and flax at this moment. And of course, this type of method been adhered by Ford, BMW, Mercedes. And let's see the fiber extraction process and composite preparation for this work. First, we got this cell extraction. You can see that picture number A. We had a complete shell after the taking out. When we cut the shell, that is the similar white portion we found. We take out the white portion from this shell, and then that's the picture number C. That is the complete shell or the things actually our raw material. Then we cut those shell into small pieces. Then later on, we use the mechanical grinder to make it a powder actually, because the conventional biofibers such as flax, jute, Remy, we can convert that one into like a yarn or like a wire type thing. Whereas for this one, it was not possible. That's why to mixture or to get a homogeneous mixture, we converted this one into particulate or a small fiber. Actually, we later on did some sieve analysis. Now let's see the treatment we do, because there is a lot of reasons to doing the treatment, because as you can see in the picture, the treated fiber looks a little bit darker than the untreated one, because in the untreated fiber there is a debris, pectin, and some other component, for example the hemicellulose, which is hydrophilic, which is not good for the material perspective. So we did the alkali treatment. That is very common, that is very common, and that is economic as well. There is other treatment as well, silane, then permanganate, but we use this one because that is very cheap. So the main purpose of this one, after the treatment, the surface become rougher, resulting is a decline in diameter and an increase in aspect ratio, and that helps actually enhance its mechanical and thermal properties. Moving forward, we can see that for this particular research, we use the ratio of distilled water, sodium hydroxide, and the fiber equal to 19:1:1. And we use a varied treatment times from 0.25 hours, which is 15 minutes to 2 hours treatment, so that we can see the variation. And but there is one thing we need to be a little bit mindful. If we do the prolonged time of the treatment, we have found that even in the literature, the properties, mechanical and thermal properties, being deteriorated. Let's see the composite preparation. We use that conventional hand layer process, and on this occasion we use only 10% Borassus husk fiber, and we included 90% of the resin. Now this resin, we use the conventional epoxy resin, because epoxy been mostly used for any kind of like this engineering application. So you can see the whole chronology of that one. I must tell you the mixture. You can see the picture number. If we did the mechanical stirring, but after that we put that into a vacuum chambers for the degassing, because there might be some kind of gas or trapped moisture. So we do the degassing process, which is not even included in the picture, but we did the degassing so that there will be no gas, or there will be no air inside or bubble. So after that we poured the all the mixture inside the mold. And yes, we followed the method provided by the supplier, how to the preparation method. So we do the pre-curing, post-curing, and that's the lookalike, the sample. And the result and discussion, actually there is a lot of results and discussion we have gone through, but I included as much as I can. There is some other, you can find this one in the reference segment. So let's talk about the properties of untreated fiber and treated fiber. Husk fiber first. We'll see the morphological properties under the ACM, then chemical analysis through the FTIR. We use the potassium bromide, and then the thermal properties via TG and DSC. Let's see the first morphological properties. You can see that the picture number A, which is left-hand side, that is the untreated. You can see there's a field over there, pectin over there, and all those oil. That's why things are covered. After the treatment, you can see in the picture number B, all this debris, pectin and wax been taken away. That's why there is a surface being a little bit rougher. We can see the porosity inside. This porosity is also good for like the insulation property. So this is the like the visual expression, and that will later on we'll see that how this treated fiber will incorporate or enhance its thermal and mechanical properties. Let's go to the chemical analysis. So from the theory, we actually know that the treatment is also, alkali treatment is also essential for decomposition, or maybe the dissolve the hemicellulose. Hemicellulose is not very good for the in terms of mechanical properties, because hemicellulose is a hydrophilic. It absorbs moisture from the atmosphere, and that actually degrades the mechanical properties. So that's why, to confirm that, we did the chemical analysis through FTIR, and you can see that I distinctly mark two the peaks. One is 1741, another one is 1255. These two peaks is a representation of the presence of the hemicellulose. However, that is the untreated one. When we did the treatment, we have the varied treatment time. You can see that that peak is not overlapped with that. That's been the hemicellulose been taken away. It was been taken away. That's that is the main purpose, one of the main purposes of our treatment. Let's see the thermal properties via thermogravimetric analysis, or TGA. I included some of the samples, if not all. So the red color is representation of the untreated fiber. You can see that there is a 3 peaks in the red color. One is 0.17. That first peak is for the dehydration peak. Second peak, which is 0.39 at that peak. That peak is the representation of the hemicellulose, and the last one, the top one, that is the representation of the cellulose. So for all the treated are included over there. There is no second distinct peak. That's been even from the TGA, we can confirm that the hemicellulose has been taken away. So that's why for the treated fiber, there is no second peak, distinct second peak over there. Let's see what the properties we got. So we got the untreated. When we have the untreated fiber, the char residue, we got 21%. I should mention that all these tests have been done to the maintaining the industry standard. And for this one, the heating rate, we use 10 degree centigrade per minute. And under the nitrogen atmosphere, the nitrogen was, if I'm not wrong, 110 milliliter. So taking back to this one, so untreated fiber got 21% residue, whereas for all the treated, it's actually enhanced. At 2 hours, it actually deteriorated. You can see that is perhaps one of the reasons, like because of the prolonged time, some of the cellulose been deteriorated. And if you see the IPDT, that is the integral process decomposition. This is another way to represent the thermal stability. This one was introduced by the Doyle. So instead of, like, for example, in general conventional, the weight with the temperature, we got like from the onset temperature, or maybe the high peak temperature, we can suggest that some reference even suggests that like 15% mass loss or 75% mass loss. From that, we can say that whether it is like more thermally stable or not. So IPDT is one of the way. Instead of those peaking point, it collectively collect all the scenario. So in the whole event, so it is a holistic representation, and we found that this value is proportional to the char value. For example, if the char value is higher, this value would be higher, but this is representation with the temperature. There is another value we found from the same curve is the IPDH. This is the parameter we've been introduced for this purpose, and we found that if the IPDH value is the higher, it's higher in a positive sense. If it is higher, its heat capacity would be lower. You can see that for the untreated one, that is the minus value, -15. So that's been because of the presence of hemicellulose. The material got the lots of heat absorbance. That's why we found this like rather than it's exothermic, it become more endothermic event. That's why the value become negative. And all those treated one is a positive. That's been become exothermic. So it is more thermally stable, or you can say that this is more providing the insulation property. Let's see the DSC. We carried out the heat capacity, a specific heat capacity, figuring out process using the DSC. So over here is the pretty much similar to the TGA, So untreated fiber being marked with the red color. The first peak is representation, again, the representation of the moisture presence, and of course the heat capacity would be higher over there. You can see that because the presence of the hemicellulose hydroxyl bond. The second peak for the untreated, that is the representation of the hemicellulose, and the third one is the cellulose. We know the lignin is a leftover, so lignin doesn't have those type of distinct peak. However, when you did the treatment, there is no hemicellulose peak present here. So within these 3 tests, actually, we confirmed that the hemicellulose has been taken out, if not all, at least is a greater portion during this process. Let's see the result. So for the untreated one, you can see that the specific heat capacity we found the maximum is 1.6 joule per gram per Kelvin. However, all the treated is got less value because of the very clear indication, because the hemicellulose hydroxyl bond been taken away. That's why the heat capacity been reduced, which is also complementing the IPDH value found earlier in the TGA test. Let's see the properties of the husk fiber reinforced epoxy. We'll see the morphological properties followed by thermal properties and thermomechanical properties by DMA. Because of the timing constraint, I did not include the flexural and other properties that is included in the article, actually. So let's see that one. These are the representative name I use for the neat epoxy, which is the use of the control. I use the NE, untreated Borassus husk fiber reinforced epoxy. UB, U stand for the untreated actually. B shape stand for the Borassus husk fiber, and E for the epoxy. Same thing, 0.25 hour, 0.25 T mean that is the treated one. So similarly, 0.5 T, then 0.75. That's been these are the our T mean the treated. These are the treated samples we use. Let's see the result. First, morphological properties, untreated epoxies via ACM. This is the fracture surface of the untreated composite, untreated fiber reinforced composite epoxy actually. So when you see that under the microscope, we have found that the fiber being placed randomly rather than in a very orderly manner. And after the fracture, there is a void creation introduced. So these are the indication of that this is a pore adhesion property, and that happens because earlier we have seen that the untreated fiber is filled with all those pectin debris. That's one of the main reasons. Apart from that, there is a hemicellulose presence. Hemicellulose absorbs the moisture, and that also deteriorated the adhesion property. So that's the representation of the fracture surface of this composite, and that we can see that later on that will affect its mechanical and thermomechanical properties. Let's see the treated fiber epoxy under ACM. You can see that all the fiber being embedded inside the resin very rigidly. Apart from that, after the breakage, after the fracture, we can see that rather than the fiber pull out earlier, it was the fiber breakage. That is the pure indication of the good adhesion property, and that affects its mechanical and thermal properties. And that is because we have seen earlier when we did the this ACM on fiber, treated fiber, we have seen the surface becoming rougher, and that rougher surface, even the hemicellulose has been taken away. So rougher surface is good for absorbing more resin, and all the porosity been filled with the resin. That's why over here we can get like a high thermal properties and mechanical properties because of the good adhesion surface. Let's see the thermal properties via TGA. I did not include any graph over here, but rather than include the whole result. So when we use the NE mean neat epoxy, the char residue is around 6.2% from the even. Similarly, the IPDT is 429. However, when we did the untreated one, it becomes 7.5. The interesting part is it got the IPDH value is negative. That's been, again, because of the presence of the hemicellulose, it still have what I should say the higher heat capacity tendency. Although all the treated fiber reinforced epoxy got the higher char value, but even their IPDH value is positive. So this is a very good indication. This parameter is a good indication. If anyone doesn't have like the DSC to figure out the heat capacity, from the TGA result, he can predict that, he can estimate that how its heat capacity of the material should be. I should mention that I use this one dedicatedly for like the biofiber, not for any other fiber or material. Let's see the thermomechanical properties, the DMA. For this particular DMA, actually, we use, of course, use the industry standard, but there is a particular setting I still can remember the hertz, 10 hertz and 20 micrometer. That was the amplitude, and the heating rate was 3 degrees centigrade per minute. And that's all. And the event is like room temperature to 150 degree temperature, depending on what type of resin we use. So from that result, you can see that when I use the neat epoxy, the TG value or the glass transition value is 84 degree. And we pick the glass transition value in the peak of the loss modulus rather than the damping factor, because the loss modulus, after that, the material become a little bit more flexible. So the loss modulus is the peak, conventional peak where we should actually take if we want to suggest the material for the structural uses. Primary structural uses, I should mention. However, if we see the untreated fiber, which is colored by a blue color, the TG value dropped to 79 degrees centigrade. So that's been material properties, thermomechanical properties deteriorated. When we incorporated the treated fiber, the maximum we can see for 0.5 hour treated fiber with the epoxy, which is 95 degrees centigrade, is an incredible advancement. However, for 2 hours, it dropped again because we found that earlier, probably because of the taken out some of the crystalline cellulose. That's why this value dropped. Let's see the damping factor. when you look into the damping factor for the neat epoxy, we found that that value is around 0.92 for the damping factor, and it dropped for the untreated fiber reinforced epoxy. However, it enhanced for the treated fiber. The maximum we got 0.5 hour treated, which is 1.12, and for the 2 hour it dropped slightly 1.08. So with this, that's mean this material can be used for structural analysis where there is a damping factor or the vibration, the impact factor is a necessary or critical properties. Let's see some other properties which we found through this research work, which is the phase angle. Phase angle, I should talk about a little bit of that one. When after the applying load, if the phase angle, change of phase angle is 0 degree, that's mean material is absolutely or completely elastic. If it is 90 degree, that is material is completely plastic. So in between, that is termed as the viscoplastic, which we actually look into that one. For neat epoxy, with corresponding to the peak loss modulus, the value was 17.5 degree. For untreated, 19.5 degree. However, for the treated, you can see that 21 and 22, which represent that this value got the higher viscoelastic property compared to the neat epoxy, and that's why that affect actually it's a damping factor value. And total mass loss, that was another property. We can predict that under that particular environment how the material will sustain its mass or capacity stability. So we can see that 0.5 hour got the highest stability, which is loss is only 0.35% during the whole event. These two are like one of the suggested properties we found from the DMA, and these all are published, peer-reviewed, and I put it down the citation 4 to 8 article, which is included in the reference as well. So in summary, we found that the untreated husk fiber exhibited high char value, IPDT, IPH value, and heat capacity value, suggests that it would be good for like competitive any natural fiber currently being used, such as jute, remi, and the flax. After the alkali treatment, hemicellulose has been taken away significantly, I should mention, because we have seen through quite of tested, and hence the thermal stability enhanced. We got the higher char, we got the higher IPDT value and IPDH value as well, although we found the low CP value or the specific heat capacity value. Alkali treated epoxy sample showed higher thermal stability, obviously, compared to the base or epoxy resin and other conventional biocomposite found in the literature or currently being used. And DMA showed the enhanced TG value, glass transition value, and damping factor value for the alkali treated fibers compared to the just raw epoxy and untreated one, indicating better fiber matrix adhesion and impact property, and that is supported by the ACM result. All the experimental results suggest that alkali treated Borassus husk fiber epoxy can be a potential alternative to conventional biocomposite for engineering structure, especially in aerospace and automotive. That was the part of my research actually. And furthermore, we can also say that incorporating this fiber can promote sustainable development in engineering to meet net zero target set in the Paris Agreement, because we are not using any kind of conventional wood. We are using the agricultural residue, which is actually left over. So for that, to acquire that, we don't need to cut any tree, or we don't need to take down any deforestation. So that's that's why we can say that it can contribute to the net zero achievement. Apart from that, as I said before, novel parameters we have found, which is one is the IPDH via the TGA. And we found that IPDH value is an inverse relation with the specific heat capacity. And furthermore, from the DMA, we found the phase angle change and total mass loss that can indicating viscoelastic property and thermal stability quantitatively. Thank you for your kind appreciation and cooperation. If you have any detailed question regarding this one, this is my contact address. You can contact me. And all those presentation I worked based on these references from 1 to 8. These are my already published article. Based on this article, actually, I drew up this presentation, and rest of from the literature and all those things. Thank you yet again for your support. If you have any question, please feel free to ask me.